So there's one geometric situation that we typically encounter, and that's if we've got 3 points that aren't all on a line together. They're called not collinear. Then there's actually exactly one plane that holds all 3 of them. Just like if we have 2 points that are different, then there's always exactly one line that goes through both of them. Now, if we want to find either a description in form of an equation for that plane or a parameterization in the form of some kind of way to list all the points on that plane, we can do that, but we typically have to do it by converting this data a little bit. So let's talk about the plane equation. To find an equation for a plane, we had a formula for that that says that 0 is equal to the normal vector times x minus p, where x is x, y, z, and p is any point on the plane. Now we've got a point on the plane. In fact, we have 3. We're kind of spoiled for choice in that direction, but what we need is a normal vector. We need something that's perpendicular to the plane. And it so happens that we can find a convenient one using a cross product. We can find a normal vector by taking the cross product of the vectors q minus p and r minus p. And so let's talk about what that's doing geometrically. Geometrically, what that does is that starts with a point P and a point Q and a point R. Now, if those are all going to be on the same plane together, then the vector that goes from P to Q has got to be parallel to that plane. And the vector that goes from P to R has got to be parallel to it. That's this vector here and this vector there. And so the normal, because the normal sticks up at a 90-degree angle from the plane, the normal has to be perpendicular to the vector from P to Q, and it also has to be perpendicular to the vector from P to R. And so when we take the cross product of two vectors like that, we always get a vector that's perpendicular to both of them. And it turns out that, well, maybe we accidentally get the 0 vector, maybe we accidentally get some degenerate case, but this always turns out to work so long as these 3 points don't lie on the same line. So that gives us a normal vector, and we can plug that back into our plane equation up here. And it's very convenient. It takes a little bit of calculation because it involves a cross product, but that is what it is. Instead, if we want a plane parameterization, a way to find a list of all of the points on the plane, then what we kind of do is we kind of use these 3 points P and Q and R, and we use them to build a coordinate grid. We say, let's say that this vector that goes from P to Q, let's call that the east direction. And let's let this vector that goes from P to R, let's call that the north direction. And then what we do is we say, okay, if I've got u and v coordinates, like say uv is equal to 2 comma 1, then I go twice as far over in the direction from P to Q and once as far up in the direction from P to R. And that lets me at some point over here. And the formula for that parameterization is given up top here. We say that the x, y, z coordinates of a general point on this plane are given by the point P plus u along in the direction from P to Q, and then v along in the direction from P to R. And so that's also a very convenient way to take this. My computer is overworked. That's awesome. That's also a very convenient way to take this triple of points and turn it into a way to list all the points on the plane. All right, that's it.